Here we are again, bungalows for bachelors. Now we are getting into the calculations. Time for some math, the favorite part. So this one's going to be pretty quick, I think, because I see one beam. There's one beam right there. Um, that's the first thing we're going to start with is where are the beams? We got to calculate the beams. We're going to do a component design of this of all of our framing, and that means that we design one component. So we design one beam or we design one hanger or one thing at a time. So that's just the way we do things. So this beam right here, we're gonna have to figure out, we're gonna figure out that beam. And I'm gonna show you exactly how we're gonna do that here. So the first thing we're gonna do is we're gonna have this here. We're gonna wanna know some dimensions and stuff. So we're gonna leave this plan open and have this available. And we're going to go over to forteweb.com by Weyerhaeuser. So this software was created by Weyerhaeuser, who creates wood products, and you can use it to design with their wood products. They kind of win because then you can buy their wood products, and then everybody wins because you know your building's not going to fall down. So you can see here, this is the, so you just create an account, it's free, and then you just um, create a file, and then in the file you've got your levels. So at this level, I would call this the first floor ceiling. So I'm anticipating everything and I'm designing in here is going to be on the first floor or just like the first floor. Kind of, you call it whatever you like, doesn't really matter. Levels are not important. They're just folders basically. So the level properties are, are you residential or commercial? We're going to be residential. Exposure category. It gives you a description of each one. So in this case, you want to know this matters for some wind. Excuse me. This matters for wind and for some items that might be gravity loaded, but also wind might matter. So you kind of want to know what you're doing in terms of which thing you're designing, but you want to try to check the one that's appropriate for your house. If you know where you're putting your house. If you don't, probably just leave it as exposure B. And if you happen to like go into a large flat open area next to water or high wind areas, then you're going to deal with this. But most of the time, your exposure B, which is just regular urban or suburban areas with numerous obstructions, the size of single family dwellings are larger. Basically, do you have trees? Do you have things around your house that are going to break up and slow down the wind so that the wind is not smashing your house after accelerating over a bunch of flat ground, right? So the mean roof height shown over here on the left, this is like halfway up the height of the roof. What is the height of your building? So in this case, we had an 8-foot ceiling and about a 5 feet peak of roof above the walls. So we're going to add 8 to 2.5 and get 10.5 here. 10.5 feet. Good to go. So that's just good. I'm just kind of setting the properties as I go here. So first floor, I'm going to create an item. I'm going to create a floor section drop beam. Now, I'm not going to actually drop the beam. I'm going to push it up into the ceiling. But the premise here is that this is the member that we want to be designing. This is the member that we want to be designing. Wow. Okay. So first thing we're going to do is we're going to name it. Now, we happen to know this is the only beam, but how we would name this, we'd go back and we'd say, all right, what room are we in? This is technically kind of the living room. And there's only one beam in the living room. So I would name it living right left. And what that means is it is the living room beam and it's running right and left. So I'd go back. Command living right left. Boom. So now when I'm going back and if I had a bunch of beams, then that would help me figure out which ones are which. I have to remember. So member info, you can put some notes in here. I'm not going to display multiple member connection as, okay, so none. We're going to leave that alone. We're going to leave most of these settings alone. Deflection criteria, you can leave it as the code minimum. If you want higher criteria, you can leave it to improved or to high, what's happening here is this number is increasing. What that means is you're having a stiffer requirement. So the typical requirement is the deflection shouldn't exceed L over 360, which is the length of your beam divided by 360 is going to be the limit for how much it can bow down in the center. So if you had 360-inch beam, you would allow it to bow down 1 inch in the center of the beam, which would be a lot. So, and we're going to leave the member settings alone down here. So we're going to just leave this alone. All this is really going to do is that in the final solutions and report tabs, it's going to tell us if it's deflected past the deflection criteria we set in the beginning. It's going to say, oh, it's over L over 360. Or if I selected a different one, it's going to be, oh, it's L over 600 or whatever it is. So that's just kind of helpful there. All right, let's get into it. Spans and supports. So you can see your beam here, and we want to define it. The blue up here is defining the load. This means a uniform load of some kind, and you'll see what happens when we put point loads and things in. But first, we got to define the supports section. So the first thing is, what's my span? That's a very important thing I got to figure out. So clear span 1-to-1 is going to be the most common thing. Sometimes if you have a continuous beam, let's say I had 10 feet here, you'd end up with a continuous beam over 2 spans, and that just changes the properties and things like that, but we don't have that in most cases. So we're going to just do a single span. So let's go back to the drawing and figure out what that is. I happen to know 9'5" happens between this part and this part, and that's a 3.5-inch wall because it's a 2x4 wall. So I'm going to take that minus 3.5 inches. So I'm going to round to 3 inches, because what I don't want to do is I want to say, well, it's about 4 inches, and then take away 4 inches and say my span is 9'1", because that's not true. That would be false. I don't have that span, and I don't want to go under the span that I have. I want to go at least over if I'm going to be conservative. So I'm going to say take away 3 inches for the wall thickness, and I have 9'2" as my span from here to here. So I'll go back to my software, and I will tell it 9'2", 9'2" inches. Boom. It also tells me the overall length of my beam because it's assuming that I have these walls here. So that's the next thing. Support 1 is the left side, support 2 is the right side. And in this case, I have the same supports. I have 3.5 inches of wall. It's the beam is going to be set on the wall, so the bottom of the beam is in contact with the wall. The type of thing I'm setting it on is a stud wall. And the material, excuse me, could be southern pine or spruce pine fir. Doesn't matter too much. Spruce pine fir, I believe, is a little bit softer, so we're going to go with that one to be a little more conservative. That's the most common. And then accessories, blocking. So you'll notice when I take this away, it takes away this dashed line that was over here. And what this means is, it means when I install this beam, I am going to make the end of the beam rigid. I'll go to my drawing here so I can draw. So when I put the beam, let's see, so this is the cross section of my beam. When I set it on a wall, I'm going to brace it laterally with some 2x4s or something so that it can't rotate either direction. I'm going to do that on the ends of the beam. That's what that's referring to. It's called blocking, and it's typically blocking is done with blocks. So in this case, they're just used in a different way. But the premise is that you are preventing the ends of the beam from rotating by restraining them. So we're going to leave blocking on because that helps us. It makes our beam stronger. And then we're going to talk about bracing here. So top edge bracing and bottom edge bracing. So along the length of my beam, if I were to do more of this blocking thing and support the beam from rotating laterally along the beam, I can hold more weight just because it makes the beam a little bit stronger. So we're specifying what is going to be the end result of this beam being attached to something. So let's go back to the drawing here. So this beam is going to have one roof brace sitting on top of it here, and it's going to have a bunch of ceiling joists. Let's say it's a flush mount beam. So it's going to sit on the walls. The ceiling joists are going to come into the bottom of the beam, and they're going to hang on it with hangers. So in this case, the top edge of the beam is just going to be floating in the attic, and the bottom edge of the beam is going to be nailed to sheetrock, and it's going to be attached with a bunch of hangers to all the ceiling joists on the bottom. So every ceiling joist is 24 inches on center. So what I can do is I can claim the top edge is at the end supports only, at the ends where I got the blocks. The bottom edge is going to be supported every 24 inches. So I'm going to say a custom length of 2 feet. So every 2 feet, I am laterally bracing this. Now I could possibly claim more because I'm nailing sheetrock to the bottom with a bunch of nails, but I'll be conservative and ignore the sheetrock. So 2 foot bottom edge bracing. So that defines all the supports of the beam. Now, how are we loading the beam? All right, so here's where we get into the numbers. So we're going to go back and we're going to ask top down. Well, what are some of the loads we know are happening here? Well, let's deal with those roof brace last here because that's a roof weight. And I'm not concerned with the roof weight that's here because it's going to be either put straight on the wall or it's going to go on the top of the beam, which is going to go straight through it onto the wall. Not going to stress the beam. So I'm concerned with this roof brace and I'm concerned with the ceiling joists over on this side and the ceiling joists on this side. They're both putting weight on this guy. So how would I account for that weight? Well, in a perfect world, what I might do is I happen to know, let's pick a different color, that I've basically got, these ceiling joists doing this, except they go all the way across. Oh, my color's changed. Oops. I got that happening. And I got them going this way as well. Now, why did I draw it only halfway to the wall, you might ask? That's because I'm only holding half of the weight of the ceiling. So this goes back to the tributary area that I was talking about before. This is why the tributary areas were important. Pick a color here. So this beam is holding these ceiling joists, but it's only holding halfway to the other side of the support. So the ceiling joist that exists right here, half of the weight goes that way to the wall, the other half goes this way to the beam. I'm designing the beam. I'm not designing the wall. So I want to know how much weight the beam is responsible for holding. The answer is the halfway point to the other support of the ceiling joists. So let me get rid of these guys here. So I should have made that stay that way. So I have a tributary area that I'm dealing with for this beam that is going to there, and it's going approximately to there. And I'm going to make a box because this is the area that I'm responsible for carrying. That is the ceiling area that this beam is going to carry. Now, remember the numbers. We decided this was not going to be an attic, so we're going to have 5 pounds per square foot of dead load, 10 pounds per square foot of live load. These are just numbers from the IRC standard. I'm responsible for this area. Now, how am I going to put this information into the software here? Well, let's look at what it's asking for. First of all, I'm going to hide the beam here so I have more reading. Okay, so load 1 is the uniform load, which is the pretty blue thing you see on top here. The fastest thing to do is do the uniform pounds per square foot. I could do a uniform pounds per linear foot, and I don't have a point load, and I don't have a tapered load. It's uniform. So if I do pounds per linear foot, it's asking me what my dead loads are in pounds per linear foot. So I got to do some math to get to that point. Well, I don't want to do math to get to that point. I just want to put it in uniform PSF. So is it the full length of my beam? Yes. Location, it's across my full length. If this was not true, I could specify what part of the beam I'm loading, but I'm not. I'm loading the whole thing. So what's the tributary width? Well, let's go back here. This is asking me for the width of the loading area perpendicular to the direction of my beam, which is, let's do this color, which is this width right there, W for width. That is my tributary width. I need to know that number. Now, I happen to know I'm going halfway from here to here, and I'm going halfway from here to here. So because geometry is the way it is, I basically know that I'm covering half of the ceiling area in this particular area. So whatever the full width of my house is, 2111, let's say 22 feet, I'm holding half of that. Just because it doesn't matter where I put this beam, I'm going to be holding half either way. If I put the beam right here, I'm going to hold a little bit of half this way and then a bunch of half this way. So it's all the same. It's all the same. So I have approximately a 22-foot wide building. So I am going to say I have 11 feet of tributary width that I'm responsible for holding in its ceiling area. So I'm going to come in here. I'm going to say 11 feet. Placement. So this is asking me where this is going to be placed on the beam. If I wanted to be really crazy fancy and correct, what I would do is I would figure out how much of that 11 feet is on the front side, how much of 11 feet is on the back side. I happen to know that it's not going to make a huge difference in my loading scenario, so I'm going to ignore it. But if you want to do it correctly, here's how we would do it. We basically figure out, oh boy, hope the computer doesn't die while I'm doing this. You know what? I'm going to pause this and fix it in post. Fuck. All right. Okay. We're back. Got the laptop plugged in. So I would figure out how much tributary width is on one side of the beam, how much tributary width is on the other side of the beam. In this case, I'm going to do an approximate because approximates are good enough for what I'm doing here because this doesn't make a huge difference. Let's say 7.5 feet on one side and then 3.5 feet on the other side. That'll give me 11 feet total. 7.5 and 3.5. So I'll go back to this. I will say 7.5 feet on the front side. Now the ceiling is 5 dead load. There's no slope to it. Floor live is also called ceiling live. So basically the same thing. 5 and 10. And I'm going to call this front ceiling. Now I need the back side of the ceiling, so I'm going to go here, quick copy load, or I can click add load and then just change all the numbers. I'm going to copy this. It's all the same ceiling load, but I'm going to say it's 3.5 feet on the back side. So now I have two loads, one's on the front side, one's on the back side, both from the ceiling, the 5 and the 10. Those are important across my whole beam. So that's my uniform load. I have my ceiling weight loading my beam in this thing. Good to go. Boom. Happy days. So what else is sitting on my beam is what I should ask myself. Well, I got this roof brace in here. Okay. Well, how do I figure out what that roof brace is doing? Well, I'm going to go back, and this is a point load. This is not a uniform load. So the first thing I'm going to do is about where am I going to put this weight? Well, I put this roof brace here on the corner of this wall because that's as far as I could get. And then I decided that the roof braces on the ridge go every 4 feet. So 4 feet over, I'm going to put more weight down. So I know that. So let's go back to here. We're going to add a load. It's a point load. And location is going to be 4 feet. It's going to do this from the left side of the beam. So when you go look here, there's going to be an arrow. Approximately, well, once I add weight to it, let's add some pounds so it shows up. So approximately 4 feet in over the 9-foot-ish beam is my point load. So let's figure out how we're going to do this. So I'm going to place this on top of the beam, most likely. Well, actually, because I'm going to place this on the front side of the beam because of the way I have to attach this particular brace to the beam, and I will describe that in a second here. So I have approximately 4.5 feet from the top here, and my beam has depth to it. Let's say it's a 12-inch deep beam. I can't set this on the top of the beam because I went up a foot. So I'm going to end up setting it on the side of the beam using a ledger or something like that, most likely, because I need the height. So I have the beam cross section. I'm going to nail a board to it down here, and then my roof brace is going to go up like that. And I'm going to nail this thing in, but it's going to be sitting on this ledger that's also nailed in. So it's going to be loading the front side because of the direction it's coming in at. So loading the front. Okay, so dead load and roof live load. These are numbers we got to figure out. Now, these are in pounds. See this unit? Point load in pounds. How the heck do I know how many pounds I'm going to account for? I'm going to call this roof brace because there's only one. How the heck do I know how many pounds I'm going to account for in this roof brace? Well, tributary area is the answer. So I need to know how much area, projected area of this roof, I am responsible for holding. Let's go back to here. I don't think, yeah, I can't put a roof slope factor here, so I'm going to actually end up tweaking the dead load just a little bit, but I'll talk about that. So how much area is this brace responsible for holding? Well, we're going to play the halfway rules. And I'm going to get some other stuff out of here so that it's easier to see. Okay, that's better. Get some things out of here. Let's get rid of that too. And the pink thing. Okay, so how much area is this roof brace responsible for holding? So the first thing is, what is the center of the support on the roof ridge? It's right there, right? So this little spot right here, that's what I'm concerned with. I'm not concerned with where I'm holding it up on the beam. I'm concerned with the ridge. This is where all the loads are being taken to on the roof, and then that load's going to go down through the roof brace to the beam. So I'm concerned with this point here. So I'm going to play the halfway game. On this roof ridge board, I have a support here, here, and here. So how much roof ridge am I holding, am I responsible for, because of tributary areas, from this center support here? I'm going to go halfway to this one, boom. And I'm going to go halfway to this one, boom. I'm responsible for holding this width of the ridge. Cool? Cool. The rest of the width is going to go over to that brace and then down to somewhere else. So I got that width. That's my width that I'm responsible for. Take that line. Okay. Now that gives me one dimension. I need an area. That's only a line. I need an area. So now, how much am I going to be holding up and down? I'm going to do the same thing. The ridge, the rafters on the ridge, start on the ridge and they run down to the wall. How much rafter am I responsible for holding on the ridge side? Well, half the weight of the rafter is going to go to the wall, half the weight of the rafter is going to go to the ridge. So somewhere about halfway, here's the rafter. It starts on the wall, comes up to the ridge. Boom. Somewhere along that halfway point is where I'm responsible. Okay. Same thing on this side. I'm going to draw my rafter right here next to my line. Somewhere along this halfway, I'm responsible. Okay. So what am I going to do? I'm going to draw a rectangle from here over to here, up to here, to here. That is my tributary area that I'm responsible, that this brace is responsible for holding. That's where all the weight's going. The weight that's down below this is going to go to the wall. The weight that's over here is going to go to that brace. The weight that's over here is going to go to this brace, etc. The weight that's up here goes to the wall. I don't care about those things. So that's the area that I'm responsible for. Now, how do I get this area into some kind of weight of pounds? Well, I know the typical weights that are assigned to a roof. 10 pounds per square foot of dead load, 20 pounds per square foot of live load. So I'm going to apply those to here. Now, the inputs are separate. Remember the load duration factors I was telling you about? Dead load matters differently than live loads, right? So the dead load has a factor, the live load has a factor. It's going to calculate all that for me, but I need to know that I'm putting these in separately. So I'm going to do the math separately. So if I have 10 pounds per square foot dead load, how much area do I have? Well, I drew a rectangle on a plan that has some pretty fixed dimensions, so I ought to know, right? What's my width of my rectangle? Well, it's 4 feet, right? Because all my braces are 4 feet on center. That's what I'm aiming at. So I have a 4-foot dimension on one side. That makes it easy. That's a 4. And then what's this dimension so I can get the area of my rectangle? Well, that dimension is half the width of the house, right? Because I'm responsible for half of that area. And I had approximately 22 feet. So I'm going to say about 11 feet here. 11 feet. So I got 11 feet by 4 feet. So the area is 44 square feet. Now my roof weight, dead load, is 10 pounds per square foot. So I'm going to take that number, multiply by 10, 440. And I'm going to take my roof live load, and it's 20. Now 20 is just double 10, so I'm just going to double my number. Now I'm going to go back to my dead load. Here's a tricky thing. The dead load is not just 440 because my roof is pitched. So what I'm going to do is I want to know about what factor should I multiply this to increase the amount of weight that I have because my roof is not flat. So I've got this cool little roof slope trick over here. So I'm going to do is I'm going to copy this just so I can use it as a calculator. And I'm going to say 100 in here so I can get a percentage factor. You'll see what I'm doing. So if I have a 512 pitch, it's going to tell me that my adjusted dead load is 108.3 pounds. So because my roof is pitched, so all these areas that I'm working with in this plan, these are all projected areas. I'm only looking top down, which is why we have to factor this because the roof is at an angle. There's more material there than just top down. So if I take the projected area of 100 something and it's got a 512 pitch, then I actually have 108.3. So 8.3% over is what I need to know here, right? That's what I did. So I'm going to take 440 with my calculator that I have, that you should also have, 440 times, let's see, we're doing an addition of 8.3%. So we're going to multiply by 1.083. We get 476.52. Go ahead and round up to 477. Perfect. So I actually have 477 pounds of dead load there. Boom, good to go. Delete this because I don't want it to actually be there. I just use it as a tool. So now I know that this weight of dead load, this weight of roof live load at 4 feet from the end of the beam from the roof brace is the load. Boom. Cool, moving on. We're not going to put any holes in the beam. We're not doing anything with location analysis or anything like that. We're going to go to product selection and guess. The way the software works is it's a guess and check. Pick something you think will work and move forward. Now this is a pretty small beam. I would like to make this out of commodity lumber because that's the least expensive thing and the easiest to work with. So 2x Southern Yellow Pine number 2 is what I'm going to check because that's most of the material I'm going to use. If you're using Doug fir, use Doug fir or whatever. And I'm going to use, so this is a 2x4 size, 2x6, 2x8, 2x10, 2x12, and then I have 2x14 apparently is in here, but I don't know if I'd ever be able to buy it. So let's try the good old fashioned 2-ply 2x10s. So I'm going to take two 2x10s. I'm going to nail them together and glue them together and make a beam out of it. Let's see if it works. Does not work. That's a bummer, but that's the way it goes sometimes. So what is this table telling me? First of all, there's red. The word means failed. I did not succeed. I can't use this. So how did I fail? Well, it's going to highlight the thing that I failed. I failed in moment. Moment is the breaking force. It's the breaking problem. My beam will actually break. My deflection is also fine. Yeah, past L over 934, and so yeah, the beam is stiff enough. You will run into stiffness problems over long spans, and you'll run into breaking problems over short spans. So beam's not strong enough. It fails 135% capacity, so it doesn't work. So I got to go back. So either I'm going to add another one and say 3 of them, and that works. I am now at 85% capacity. I still have plenty of stiffness. I have no stiffness problems. So 85% capacity, good to go. Or if I'd rather only install 2 boards, I'm going to go to up to a 2x12 size, try 2 of them, and I still fail. So in this case, it's probably most economical to do 3 2x10s. So that's how we do it. We just kind of guess and check. In this case, it was a simple beam, so everybody's happy. So what do the other things mean here? So the member reaction on the bottom is telling me what is the weight at the location of support. So I have 1,396 pounds predicted total load at the end of the beam, and I can put 6,694 pounds on the wall based on the width of my beam and the amount of wall thickness I have. And what that means is, am I going to crush the wood on the wall with so much weight that it actually like squeezes the wood fibers and crushes it? And the answer is no. I am only at 21% capacity. I'm fine. And then shear is another way that beams fail. It's more complicated and doesn't happen. Usually this is like not the thing that makes beams fail. I'll talk about special shear case later, but most of the time we don't have to deal with this. So it's always going to be fairly low. And then moment we talked about, that's the breaking, that's the bending. And a live load deflection is if you applied all the live load, what's the deflection of the center of the beam? If I applied all the total load, which is live load plus dead load, what's the deflection? If you want to know what the dead load deflection is, which means theoretically when the beam's installed, all the dead load's in place, but there's not much live load, what's my deflection? You would just subtract the difference between these two numbers. So that's it. That is how we define the beam. So now 3 pieces of 2x10 Southern Yellow Pine number 2. So I'm going to go back to my plan, and I'm going to say this beam is 3 ply 2x10 Southern Yellow Pine number 2. Okay, so now I've got it notated on my plan. I'll write this out, however you want to write it out. So that this is what I need to use here in order to know that I can hold the ceiling and I can hold this roof brace. And that's how you design a beam. This is only one. Normally this is a time-consuming process, but that's it. So once we got the beams taken care of, what else is next? Well, what are the hangers? Are there any beam hangers in here? No, there's no beam hangers, so I don't have to deal with that. Post sizes. Do I have any porches or patios where I have an exposed natural raw post or anything like that? No, I don't here, so I'm not going to worry about that. If I did have that, I would want to know also what is the post cap type that I'm going to use? What is the metal hardware that's going to allow me to connect that to the rest of my structure? I'd want to find that. Built up posts. Those are those go in the beams. Sorry, not in the beams, under the beams. So this beam is going to sit on the wall. In this case, it's going to sit on a corner here where there's already going to be lots of studs, so it's probably fine. But in this case, it's going to be sitting on a wall, and there may or may not be a stud below it. So we need to figure out what we need to put studs below it. We need to fill it up, but how many studs do we need? That's the question. So we can check that with math. We can use our software. So what we do is that we do the same math for either end. It doesn't matter because it's symmetrical. Actually, that's not true. It's not symmetrical, and I will show you why, because this roof brace is not in the center. So we're going to go back. Now, if I go all the way to report, it's going to give me more information. It's going to show the thing. It's going to show the same table. It's going to show me my support reactions. It's going to show me some other things on weight. Now, what I want to know is the supports. So this is the left side support, which is support 1. I had a total load, a factored load of 1,396 pounds. And the right side was 1,185 pounds. So those are different numbers, right? Because this weight is not in the center of the beam. If it was in the center, they'd be equal. But if I put the weight farther to the left, it's going to put more of the weight on this side. So This is the number that I want to use. These are numbers that are important to me. Now it's got these still separated out and dead and live because we have to keep them live, keep them separate. Sorry. So there's dead load, there's floor live load from the ceiling, and there's roof live load from the roof. So I want to take this weight and I want to put it on a built up post. Well, I can make one of those here. So I'm going to go to my new member and I'm going to pick a what do they call this? A wall column. I believe this is the thing I want here. Applies, yes. Okay. So wall column. So I'm going to call this. We'll do both sides just so you can proof of concept here. Left side of beam. Well, there's only one beam here, so we know what we're talking about. Okay. So member notes. You could write notes and you want. Wall deflection criteria. Okay. So what am I covering the wall with? Because what I'm really checking here is when I put weight on this stud, it's gonna try to like bow, basically. It's gonna try to buckle. So depending on what finish I have outside will tell me if I need stiffer criteria or not. So if I've just got if it's an exterior wall with flexible finishes like wood, things that can shift, it's not as important. If I got plaster or stucco, I need it to be stiffer because I want to crack that. And then L 600 is just like super stiff, right? So I have an interior wall here, so I'm not concerned with anything. I'm concerned with like kind of the standard um, exterior wall with interior gypsum board finish. Gypsum board is drywall, sheetrock. So I'm going to go with that one because it's the sheetrock that's the factor that I'm concerned with here. I don't want to break sheetrock. So height and supports. What's my wall height? 8 foot. I don't have to be super exact here. That's just good enough because it's the total wall height. I have two top plates, a double top plate, and I have a double 2x top plate that's made of southern or spruce pine fir, and I have a bottom plate that's a 2x material of spruce pine fir. I'm going to put. Am I going to put fire blocking in this wall? Well, when I like to frame even 8 foot walls that don't require fire blocking, I like to put a midway block somewhere in there. So there's actually going to be a block in there. But this is asking what's the unbraced length of this thing. Well, in our case, worst case scenario, the maximum unbraced length. If this is an exterior wall and it was getting nailed to like structural sheathing, like OSB or plywood, we put wall sheathing nailing because when it gets nailed to that, that's very stiff. In this case, we're going to leave it as fire blocking. So maxed unbraced length is 7 foot 7.5. So we're going to leave it alone. It's fine. So loads. All right. So if we were to load a column in the exact center of the column, we would theoretically not having any possible buckling issues. But because nobody cuts everything perfectly and like the loads are never transferred perfectly like this, we have what's called eccentricity. Now, the 1/6 of side dimension is the standard when we're talking about like designing for the future. So I'm going to design this assume that my load is offset somehow 1/6 from the center. It's going to cause a certain buckling load. So that's what I'm going to go with. I can change this if I need to in the future, but most time I'm just going to leave this as 1/6. So what is the tributary width here? This is asking for why does it want to know like the tributary width of my wall? Well, it's because this might be like wind loaded, right? So do you see down here? There's a lateral load and it's got a load in here. Load 1 is uniform, location, full length, wind, see report. So it's saying the wind is going to load my wall. This is assuming it's an exterior wall. I don't have this case. So I'm actually going to delete that. I don't have that. So if that's the case, I don't care about my tributary width. That's the only time that would matter. So I'll leave it alone. So I have a point load inside that I'm setting on top of my post. That's what I'm concerned with. So I'm actually going to delete this because this is a manual way of entering weights. I'm going to delete that. I'm going to go to this arrow. Come on. Didn't work that time. Weird. Okay, add load, whatever. So I want to link a reaction. I'm going to go to my living room beam. I want reaction 1 or 2. Well, I'm going to do the left side of the beam, so I want reaction 1. So select one, it's a point load, transfer to vertical loads. Boom, done. So what I've done is I've taken the end of the beam and I've set it on this post, and I didn't have to do anything. I didn't have to do any math. It pulled the information over, and I'm happy. Moving on, because I got rid of the wind load. Product selection. All right, commodity lumber, 2 by Southern Pine number 2, or Spruce Pine Fir number 1 or 2, depends on what you're kind of building your walls out of. Most of the time, let's go with Southern Pine. 2 by 4s, because I got a 2 by 4 wall. If I use one stud, can I put the weight of the beam on it? No. The answer is no. We got failure here in multiple ways. Okay. How about 2 of them? If I put 2 studs together, am I good? I'm good. I pass, and I pass well. So a double stud would be good enough to hold the end of this beam. So I'm happy. As long as I have 2 studs, I'm happy. Now, the general rule of thumb is, the general rule of thumb is you want your stud, you want solid wood from your beam all the way to the foundation. So if my beam is 5 inches wide, I would have to use 4 studs to get at least as wide as my beam in the wall. That's the general rule. But you want to check to make sure that's still enough. Sometimes you need a 2 by 6 wall instead of a 2 by 4 wall for the load capacity. But in this case, 2 studs, I'm good. So I'm going to stop there, go back to my drawing, and then add a call out here. On this side, this is a corner, so I am almost definitely going to have 2 studs. But on this side, I might or might not. So I'm going to create a call out here. So 2-ply post minimum. So I know when I'm framing this one wall, laying out these plates on the ground, when I'm getting ready to frame this wall, I'm going to have a door, I'm going to have a corner, and I'm going to have a beam with a 2 stud laid out just in line with this wall so that this beam can land on it. I'm going to do that all in advance so I know that that's there. Okay? So that's one of the things. If we got more beams, we would check more things, but we don't. So we're good. All right? So now we're going to look at our header sizes. So what else do we have in here for headers? The basic way to do this is you could, if you really wanted to go crazy, you could design all the headers in here. You go in here to a wall header member and you design it. That's kind of unnecessary because there's lots of header tables in the IRC. Basically, what you're going to do is you're going to go through and you're going to pick these out. What case do they apply to, and how are we loading them and stuff like that. So most of the time, you can get away with a 2-ply 2x6 header when you're being loaded. Sometimes you can get away with like a 2-ply 2x4 or no header at all, just a flat board if there's no weight at all on your thing. And when that's going to happen is situations like this header here, because I know my ceiling joists are going up and down and I don't have a roof brace on this thing. So there's literally just going to be wall and no weight on it. So there's no weight there. There's no weight there. Now this one is going this way, which is perpendicular to the ceiling joist. So I'm going to have some weight on it. In fact, I'm going to have a little more weight than normal. I got attic. So a 2x6 double header would be probably a good idea for that one and that one. And this guy is a regular, it's a little 2-foot door. But again, that's close to some roof braces and the ceiling's going this way. So let's make those, double 2x6, double 2x6. In general, you'd want your exterior walls to kind of always be a double 2x6 header just because you're going to have more stuff going on the outside of your house. You're almost always going to have roof on it, right? So double 2x6 headers there and there. There's another one that could probably be a 2x4. Nothing crazy. That one also double 2x6. This one double 2x6. Even though it's wider, like I said, it's supported in the middle, so it's okay. It's still strong enough. So we'll do the same thing. Check the spans, check the tributary widths, check the areas. This one is a wider one, but it's in line with the ceiling joists. So again, this wall is literally that's not true. So it's going to have some weight on it actually, because there's a transition here in the roof shape. There's going to be some framing on here. Even though there's not going to be a significant amount of weight, there's going to be some. So this might end up being a double 2x8 or a double 2x10 simply because of the span here and a little bit of weight. And then this guy over here, this guy's holding a roof brace and it's holding a bunch of ceiling and it's kind of wide. So this could easily be, a double 2x10 header. So we're gonna check all those things. In this case, you could design this if you wanted because that's a very specific weight coming down. We know that weight would be the same thing as the one we did over here. So we would just copy the work we did and put it on the center of this header if we were designing it in Forte. That's how we would do that. But we'd label all our headers with their sizes, and that's how we would do that. Just reference the IRC for tables or design them in Forte. Tall wall studs, we don't have any tall walls in here because it's 8-foot ceiling all the way around and there's no vaulted ceilings. So we don't have any problems with that. If we had tall wall, what is a tall wall? A tall wall is technically anything over 12 feet tall by different people's standards, but mostly 12 feet tall because that's when you start getting out of the pre-cut stud lengths and you start to have special things going on. We don't have that. We got regular walls. Gable bracing. Okay, so the left side of this house has an exposed gable. The right side of the house being tied in somewhere else, so I'm not concerned with that. So on this side, I have this gable wall here. Well, what I need to do is I need to make sure that this gable wall isn't going to buckle, under a wind event, which is technically in like the wind category, but it ends up in the in the gravity sometimes. But the basic premise is this wall. If I were to draw a section of the wall, I have an 8-foot ceiling. There's my ceiling line. There's my 5 feet of attic. There's the peak of my roof. There's my foundation. The wind's going to blow on this from the outside, right? And if I don't have support right here, this thing is going to buckle inwards like this and break and fail. We don't want that. That's what we're trying to avoid, right? So what we're doing is we're looking at this whole wall that's being blown by the wind, and the same thing applies with suction. Suction happens too, can be pulled outward. So when the wind blows on this, I have support on this wall, I have support by this wall, and I have support by this wall. I don't have support here in the middle here. What I want to do is I want to try to support this thing every 6 feet, right? So my closet is 7'5". That's kind of close enough to not really worry about it. It's not a big deal. And then in here, I've got 14'6". So I'm going to add two supporting lines here. And the way I'm going to do this is there's a detail in the wood frame construction manual from the American Wood Council on how to add blocking in the ceiling joists and strap it to the wall such that you can, basically support this wall. So what you're going to do is you're going to basically add a block between each ceiling joist, some distance back into the wall specified by the table in the book, right? You're going to add those blocks in. And then when you get to the wall, you're going to take a metal strap and you're going to strap it from the blocks and you're going to run it down the wall, like down vertically, not, I can't show it on the plan view, but like down vertically onto a stud. You're going to strap it down so that way it also provides against strength against suction when the wind is pulling the wall this way. But you're going to do that. You're going to block into the ceiling. And what that's going to do is the ceiling diaphragm, when the house is built, is actually like quite a stiff structure, right? So I've got the 2x6s that are creating the ceiling joists. I've probably got a board running across them to space them out and keep them stiffer together. And then I also have them all nailed together with sheetrock. Sheetrock can be considered a structural material. So it's stiffening this whole diaphragm. So by putting these blocks in and then tying these all together, right, with a 2x4 on top of all the blocks, I'm gaining the ability to. It's like I have a wall here. It's like I have stiffness added to my wall so that the wall can't blow it in. The wind can't blow my wall in, right? So I'm going to do those tricks when I need to, but that is something that needs to be done. And the outlookers, I'm basically going to want to know. Again, I'm going to check the wood frame construction manual for the outlookers that are going to stick out over the roof. I'm going to actually go to the other page for that. Where's my mouse? So I've got outlookers in here that are going to, oops, no, I'm not going to do that. They're going to do this, right? They're going to stick out. So basically what I want to make sure is that when the wind blows up on this wall and tries to push the roof off, these outlookers aren't going to get ripped off. So I got to check some tables and things in the wood frame construction manual as well, and I can go into more detail on that in person or a Zoom call or something, but not in here. So that's how I would check those things. And then hurricane ties are basically, I'm concerned with the ends of my rafters, right? So I got a rafter coming down, rafter coming down, rafter coming down. I want to make sure that the wind blowing this direction, that's going to blow up the wall and try to rip the roof off, is not going to rip it off because I either don't have enough wind to worry about it, or I have a hurricane tie here. So there's ways to check those things. But we're going to check for those. But that's going to conclude the calculations part. And we will do a few other